This is the second workshop on CellOracle, our tool to dissect cell identity via gene regulatory network inference and in silico gene perturbation. And last week, we went through how to pre-process your data to infer gene regulatory networks. And this week, Kenji will be leading us through the second part of the pipeline. Kenji.
Okay, let's start. So please let me just briefly talk about the what we are going to do. And so the last presentation I talked about the overview of the CellOracle, and I talked about how to process your data, your single cell RNA-seq data and your single cell attack-seq data. So today we are going to use this information and we are going to get your gene regulatory network. So just brief reminder, our platform CellOracle will use the single cell attack-seq data to get the potential regulatory candidate gene. And we are going to use the genomic DNA sequence to get the binding partner of this binding candidate of this transcription factor. So today we are going to use this information. This is base GRN, but we also use the single cell RNA-seq data because even if we get like these binding candidate gene, we do not know the this gene is actually regulate the target gene. I mean, having the motif doesn't always mean it is active. So sometimes the motif is kind of the pseudo motif, or sometimes the gene transcription factor is not expressed or something. I mean, we need to pick up active active connection like this. So in this process, we are going to use single cell RNA-seq data, and we will use kind of like machine learning model. Using this model, we will pick up an active connection, and we will do this modeling for all gene, and finally we get whole gene regulatory network. Okay, so let me start using the notebook, Python notebook. So, okay, so this is the Python notebook of the gene regulatory network inference. So you can find this notebook on the web documentation here. So here, network analysis. Today we are going to use this notebook and just so first we will import library, and one important thing I want you to do is to check your installation. I mean, please run this this function. So I mean, in the network analysis, we are going to use our package. So I mean, so we need to make sure your computer have this library here. If you get some error, please go back to the installation part of the web documentation. So, but it's this saying it's okay, so we can go next. Okay, keep going. And so the first we need to import. Sorry, we need to load our single cell RNA-seq data, single cell RNA sequence data. So in the last session, we talked how to process your data. So please leave your data here. And one more thing we need to lead is the transcription factor binding information. In the last session, I talked about how to process your text-seq data and how to get your transcription factor information. If you do not have your single cell text-seq data, I said it's still okay because we provide kind of built-in transcription factor information, which was made by the many mouse tissue. I mean, I use the mouse text-seq address dataset, and I got the like general based GRN. So you can just use this one if your single cell RNA-seq data is mouse one. If you have human dataset, and in that case, you need to prepare your single cell. You need to prepare your transcription factor binding information by yourself, because we don't have currently we do not have the human text-seq dataset. Okay. Anyway, so you can easily load the transcription factor binding information with this function. Yep. So this is the kind of data frame. So this is the peak ID and gene short name. I mean, for example, this target gene have the binding information for this transcription factor, and so on. Okay, we will use this information. And okay, so the next, so first we need to make the Oracle object, which is our custom object. So from now we are going to build our date of our object, that our information is stored in this object. Okay, so first we need to check our single cell RNA-seq data first, this one. So I mean, in the CellOracle, we are using this. I mean, we are using the Python library scanpy or scanpy, so which is the store in this object and data object. So if you do not know what is this object, what is and data, please go to the scanpy documentation, so you can find much more information. So basically, our single cell RNA-seq data information is stored in this object. Okay. So first, let me check the.
Kenji, last time you mentioned that you can easily convert between Seurat and the data format.
Yep. So if you have the Seurat object, you can convert your Seurat object into this object using some function. So yep. Okay. Next, we are going to check the kind of metadata, because we need to use like cluster information or dimensional reduction information or something. So first, clustering information is in this object and data.obs. So I mean, you can you can visualize, you can check your metadata of your single-cell RNA-seq data. So here we have several clustering results like cell type and for this one as well. We made this this annotation in the last session. Okay, so I mean, today we are going to build our. We are going to get single cell. We are going to get the gene layer network for each cluster. So I mean, you need to have clustering information in this data table in advance. Okay, so you can check the metadata using this code. We also need to use the dimensional reduction data, which is not necessary for the GRN inference, but the next part in the simulation, you need these information. You need the dimensional reduction or like trajectory map or something. So please make sure you have like such dimensional reduction data. So here we have like these dimensional reduction map. So here in this session, we are going to use this data, the graph FA, which is the force directed network dimensional reduction. Okay, so okay, let's go back to the Oracle object. So we need to do is the import and data into the Oracle object. We can do that with this function. So the important thing is please enter the name of your dimensional reduction and clustering data here first. Okay. One more thing, we are going to use the low mRNA count here. So please make sure, I mean, you have low mRNA count. Usually you have the lower RNA count in this attribute. So sorry, this is kind of low, but a little bit transformed into, sorry. Anyway, we need like non-negative gene expression data here. Anyway. Okay, so.
So Kenji, in terms of the input data, and maybe this is something the group can discuss. So you need that non-negative expression data. So you can't use scale data. You can't use some of the batch corrected data.
Exactly. Yeah. So we have one option, but I honestly don't recommend. So for example, we have like function like import data as import. We can import the normalized count data with this function, but honestly I don't recommend that. So usually I use this function import as a low count, I mean non-negative, and not as scaled or not centered data. I mean, in the future, we will try to use the batch collected or something like that. But currently, I haven't checked, I haven't tested such data sets. So my recommendation is to use this function and to use a relatively low value. Okay. So next, we need to import the transcription factor data. We have transcription factor binding data like this. So we can import this data into the Oracle object with this function. So, but okay, it takes maybe 15 seconds. Just wait. Okay, so if you finish importing, you can check your transcription factor information. So, I mean, the information was converted into the dictionary. For example, like this. In this dictionary, TF have like many. Or this is the dictionary. I mean, the dictionary key is the target gene name, and the dictionary value is the list of the layer J candidate gene. I mean, if you want to know, for example, albumin, so I mean, if you want to know the target gene of the albumin, you can check like this. Maybe these factor like HNF4, HNF4G, or I don't know. These factor is the candidate, sorry, the layer J candidate gene. I mean, this gene albumin promoter have the motif of this factor. So okay, but the one most useful function is, I mean, sorry, one more thing I want to introduce is we can add any information manually. For example, yeah, for example, in the if we have like we have the if we know, for example, this translation factor CBP alpha have the target gene of this. If the CBP alpha have these target gene, we can use this such information, and we can import this information into our Oracle object manually. So this is the supplementary data of this paper. So we can import, we can use this information for the, like, for example, we need to get the dictionary instead of such data frame. So you can convert this data frame into dictionary, like using this code. I mean, if you are Python Python coding, you can do that in your way. So the important thing is we need to get dictionary like this. This is the target. The dictionary key is the target gene, and the dictionary value is the list of the layer gene, like this. So if we get such dictionary, we can add this dictionary into our dictionary. This one. We can combine this manual dictionary with this dictionary using this function. It's very easy. Okay, so so now we are ready to start, but we need one more stuff. So Oracle used the, I mean, in the simulation part, the next part, we are going to use this Python library, Verside or Verosto. So we need to do some pre-processing for this library. I mean, for example, we need to do like imputation, or we need to do PCA again. This process is not necessarily for the GRN inference itself, but we need this process for the next next simulation part. So we will do that now. So first we need to do PCA, and we will pick up the, like here we did PCA, and we picked up first 45 piece principal component here. You can just run this function without changing anything. So just do that. Next, we
How
need
do you
to do
decide
the.
on 45, Kenji?
Oh, yeah. So this is the code of the bear site. So in this function, you are going to look at this curve, information curve. So maybe the first few component is really informative. So I mean the accumulated information will going to increase really first. But here the 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 you know the slope of this curve going to be flat, and this means your principal component is going to be less informative. So based on this curve, you will decide the code will decide the number of principal component here.
I had a question, Kenji.
Yep.
So is this PCA performed on a normalized count, or is this normalized data now? I might have
Normalized count.
Okay.
Sorry, I did not explain about it. So first, we imported the low count, but if we import the low count, maybe we can show some. So can you see this? This is the source code of CellOracle. When you import the data, the inside the Oracle object, your data is going to be transformed into like log transform. So the low data is stored, but your data is also going to be transformed into the log transform.
Okay.
So the PCA was done based on your log transformed data.
Okay, thanks.
Okay, yeah. So, and then you need to decide some parameter for the KNN imputation, but we have some
Kenji, I'm
functions.
still for the selection of like 45 in the previous step. So
Yep.
if we were using Surat, for example, and that uses a similar method to select the important PCs. So I'd usually go between 10 and 20 based on a curve like this. So why select 45?
Yep. So the PCA is important for the step KNN imputation. So we will use this information just for the KNN imputation, not for anything else. So here we are we pick up the number of PC component based on this threshold. The 0.002 is the default parameter, which was decided by the library of the Velosto, this one. Hopefully this is maybe I think this is gonna be the best PC, and this value, the best value for the KNN imputation, I guess. So,
okay, so what you're saying is I should go read the Velocito stuff in more detail.
Yeah, I think it's kind of maybe you can find more information. So,
Okay.
but if you want to use if you use the PC, 30 PCs for your analysis, you can do like this. Maybe your KNN imputation will a little bit. This depends on this number, but you can try your you can set any number. This is just, I mean, this function is just kind of suggestion. I mean, if you know the first 30 PC is really good for your analysis, you can do that. You do not necessarily stick to this function. So you can just ignore here and just do that. But
Okay,
I
got it.
do not recommend like the number PC is 2 or like 3 or something. Maybe your imputation going to be really bad. So please don't use like really small number. Like do like more than 50 or 20 or maybe something like that. Okay. Okay, so we need to decide the parameter number of cells for the KNN imputation as well. We need to pick up the number k for the KNN imputation. So usually I recommend using this function. This function will decide the number of k based on your number of cells. Okay, so if you want to know more information, you can read the paper. Okay, anyway, let's do again an imputation. The imputation takes some time, takes a long time if your data is that big. But here our data is not too big, so it's finished soon. Okay, so you can say.
What was the objective of doing KNN imputation again? Like, why are we doing that?
So for the next part, we are going to for the next part we are going to do the simulation based on the GRN inference. So on the simulation part, we will use kind of function of the velocity over velocity. The RNA velocity analysis. So in the RNA velocity analysis, we will do the okay. Let me use some. Oh yes. So in the RNA velocity analysis, the first step is we will build mass model based on the spliced RNA count and unspliced RNA count. So I mean, we will, based on the spliced and unspliced count of mRNA, we can predict the future gene expression. And if we can predict the future gene expression, we are going to compare the future gene expression with the existing gene expression. But if we compare when we build the mass model or when we compare the gene expression, please imagine that we have a lot of drop-off or a lot of the noisy count. Maybe we will get really, our comparison or our mass model going to be really bad. So we need to do imputation in the first part in order to get like more better result. Especially in the first part, we are going to use we are going to know the number of the spliced count and number of unspliced count. But please imagine that if your data have like a lot of dropout, maybe your counting is really inaccurate, and you're going and in this model, the ratio between the unspliced and spliced count is really important. So, but the ratio going to be really um, we need to get um, we need to remove the dropout first. So this is why the imputation is necessary for the earned velocity analysis, and the imputation is important. Necessary imputation is necessary for our analysis as well.
I see. Thanks.
Yep. And maybe you can use any other imputation method, but maybe this is you should use the same imputation algorithm as the burst, though, because we are going to use this code.
Just to clarify here, Kenji, we're not actually using that the spliced, unspliced information, transcript information for our simulations. Just to clarify that, but we do leverage aspects of that platform.
Yeah, exactly. We are not using spliced count or unspliced count. So in the earned velocity analysis, they use spliced count or something like that. But in our analysis, we are going to use gene-related network information instead. So we just use some function, the visualization function or simulation function. Okay. So the next part, we are going to calculate GRN. So here we have like many small cluster in this data set. Or we have like sorry. Okay, so it's already started. We have like many cluster here, so we are going to build gene-related network for each cluster. I mean, if you have 10 clusters, we are going to build 10 GRN. So it takes like a little bit time. So here we can use this function oracle.getThings, this function. So we are going to calculate cluster GRN. You can set your cluster of interest here. We have some parameters, but now you do not to change here. So first you just use this function, and your information, I mean your GRN information will be stored in this object, links object. Okay, we have like 25 or 26 or many cluster. So like here, please look at this value. The GRN inference takes like 1 or 2 or 3 minutes for each cluster. So, but we have many clusters, so it takes maybe 20 minutes or 25 or something. I mean, it depends on your data, your data set. If you have much more cells, it's going to be long, and if you have many clusters, it's going to be long. But if you have like less cells or less clusters, maybe it takes really quick. Okay. Yeah. I've already calculated some cluster. So it takes 20 minutes, and I do not want to wait for 20 minutes. So I've calculated the I've already done this calculation and saved here, but I occasionally overwrite the data here. So I mean, maybe we need to wait 20 minutes now. Okay. So, but it's okay. We can stop here anyway. Okay. So anyway, if you finish the calculation, if you finish GRN calculation, your information will be saved in this object, links object. So now we don't want to wait for like 20 minutes. So we load already calculated links object, this one. Okay. If you finish your calculation without any problem, your GRN inference will be saved in this dictionary links dict. So this is the dictionary. You know, the dictionary of the key is the name of your cluster. So if you want to know the GRN of this cluster, for example, you can get the GRN like this. So this is the regulatory gene. This is the target gene. This is the connection strings. The negative value meaning negative value is it had a negative effect. Maybe this transcription factor is suppressing this target gene. But please keep in mind that you have like p-values. So if your connection have like high p-value like this, maybe this connection is just kind of random or like noisy or something. So don't use the connection if your p-value is high.
How do you select a p-value cutoff for this? And maybe Christy has some thoughts on this as well.
Yeah, usually like we can.
Hi, Christy.
Hello.
I know this is something you've thought about as well in terms of the p-value cutoff.
Yeah, selecting the cutoff can be challenging. So I've done multiple corrections, several different methods, but haven't come up with a concrete answer to that quite yet. Kenji, do you have any?
Yeah, maybe there is a method, but I mean, for example, you can, maybe the most simplest way is just pick up maybe the most simple way is just sorting this connection based on the p-value and just pick up the top genes which have low p-value. Or you can do something else like using the force negative rate or something like that. Yeah.
I remember, Christy, you were looking at the distribution of the p-values as well. And did that throw up anything interesting or anything obvious? I presume not from your answer.
No, so I was trying to make sure that the distribution wasn't terribly skewed. And when it came back looking okay, I moved on.
Okay, got it.
Okay, so yeah, maybe this is gonna be challenging how to pick up your important how to set the threshold. So anyway, let me move on. Oh, before moving on, so if you are really familiar, so if you have the skills for the network analysis, or if you want to use totally different platform, you can export your GRN with this function, and you can save your GRN and you can analyze this GRN by yourself. I mean, so Oracle is the GRN inference algorithm, but we provide some function for the network analysis. But this is just network. You can analyze this network by your own. So, like using the using many other algorithms. Okay. One more thing is we are going to visualize network result like this. So we will sometimes you will saying like you want to change the order of this prop, like you're going to order the cluster based on your preference. So you can look at this value links.palette here. So you can change the color of the visualization here, or you can change the order. For example, I want to change the order a little bit, and you can do that. So just change the information on this data frame. Okay, this is not necessary. I mean, this is just option. So you can skip here if you're not interested in the visualization part. Okay, so here we can filter the links based on something. For example, you can filter the edge based on your p-value, or you can filter the links based on the strength of your network connection. So the default parameter is like this. We just do the filtering based on the p-value first, and then we will pick up the top 2000 edge or top 3000. You can change here a top edge based on your network strengths. I mean, your network have many connections, so I recommend you to remove the connection before doing the network structure analysis. And this is
just to clarify the difference here between uncertain and weak edges. So my understanding is that they are the same. You're just filtering them out with different methods. Is that correct?
Oh, yes. I'm saying that the weak connection mean the absolute value of the connection is small.
I see.
The uncertain connection mean the p-value is very high. So I mean, we have just we have two criteria, like strength of the network and p-value. So you can use these two information for your filtering.
Thanks.
Yep. Okay, so here we just do the really simple filtering based on the p-value here, like this, and the number of connection here. So next, the first thing you can look at is maybe this one, degree distribution. I do not explain the detail of this value, but the degree means the number of edge in your network. So for each dot is each gene. single dot means gene, and the k, the degree k means the number of connection, but it's normalized. Okay, if we look at the degree distribution, hopefully you will get the like such curve. I mean the linear curve when you look at the log transformed value. I mean such network degree distribution, meaning your network is scale-free network. So which is maybe the same for your network. Okay. After checking the degree distribution, you can go to the next network analysis.
Kenji, in terms of the degree distribution for a second, what should you do if you don't see this linear relationship? I mean, could that mean that you don't have enough cells to build to infer your networks from? Does it mean if you have poor quality data? What can you do?
Yeah, so there is a main two possibility. The one possibility is maybe your network is not scale-free. I mean, which is not that bad thing. I mean, sometimes your network gonna be like non-scale-free. I mean, scale-free network structure. I mean, which is not bad thing. So maybe you can go to the next step. The many biological network tend to be scale-free network, but not biological net. I mean, not this.
Okay, yeah,
I mean, this
yeah.
is not the necessary stuff. Okay, the second possibility is your network inference is bad, or I mean, like you said, maybe your data set is poor quality or something. So, but maybe you can change this. You can look at your network here, or you can change the network threshold value here. If you change like threshold value, your distribution will change. So I mean, please look at make sure you're setting the appropriate parameters. I mean, you are setting like a really crazy p-score. Your network distribution is gonna be very crazy. I can see here.
So
you can change this one first.
Certainly with the networks we've inferred, we see these linear relationships with the degree distribution. So I think the safe assumption is these should be scale-free networks because they most commonly are in biological systems. So then if you don't see this linear relationship, then go back to these thresholds and really assess, have you been too lenient? Can you change these? Okay.
Yep. So, okay, next, we are going to get many network score like this. In general,
Kenji, I think we've lost you on the audio. Can anyone else hear Kenji right now? Oh, yeah, you're back.
Oh,
I can hear you now. Now you're muted. There we go.
okay. Can you hear me?
Yes.
Okay, yeah, maybe now it's fine. Sorry, I don't know why, but it's something wrong. Okay. Okay, let's go back to the code. So we can calculate network score using this function. So this function doesn't have any parameters, so just do it. It's easy. So if you got some error here, maybe this means your R library instruction is not well. So I mean, please go back the first part and check the R library instruction, because this function use some R library, so please make sure your R library instruction is done. Okay, so if you finish this one, your network score is stored in this data frame, for example. So you will get many network score here. Okay. If you want to learn, or if you're interested in this one, so maybe please read our paper or Google. So I mean, there are so many scores. I do not have enough time to explain all of them. So, but we can show some example how to analyze this score, network score. So first, the important thing is we get network score, but we have the gene regulatory network for many clusters. I mean, for example, here we have like 25, or I don't know, many. Like if you have 10 clusters, you get 10 GRN. So it means that you have many cluster score for 10 for each GRN. I mean, which is really huge, and maybe it's not easy.
Kenji, I'm thinking that this is such an important concept, and it's such an important part of CellOracle, is how to actually interpret this data. So maybe we can come back to this next week in further detail and like really take a deep dive into it. Because I also think it's super interesting stuff as well to discuss some of these metrics, and then we can maybe also show examples from the paper, like how we've interpreted these scores, what they mean, how the users can interpret them as well. Because I've definitely got some questions about the network inference up to now that you've discussed. So maybe we can kind of get the group involved and have a discussion about some of the considerations to make.
Yeah.
Sorry, does that sound okay?
Yeah, it sounds perfect to me.
No, it's okay. It's because I keep interrupting you, so
taking longer. It's the longer time than my expectation, so maybe it's good to spread over.
No, we're on lockdown for a while, so I don't think this is too much of a disaster. So so going back to so a couple of things I was thinking of is the normalization, and I always keep coming back to batch effects as well, and thinking I think it would be really interesting to take non-batch corrected data. So take a data set where we know there's batch effects and these clusters separate when they should actually, the cells should cluster together. What do you think would happen if we ran the network inference, ran CellOracle on those data sets? Do you think essentially that would generate two very similar networks? Do you think the batch effects could be effectively kind of ironed out under those circumstances? Or do you think we'd actually get some insight into what the batch effects are by constructing these networks on non-batch corrected data?
Yeah, if you have two, like for example, if you have two data set, but two totally different batch, if your biological system is same, maybe hopefully you will get the really similar network. But yeah, maybe I guess you will have some kind of difference because of the batch effect, I guess. So I think which is kind of good to analyze the difference between different batch, and maybe you can know what is the common or like the general network structure. So, but worst case scenario I'm concerning is like in the first process you will do the clustering, and maybe you will get the one. So for example, if maybe you will get one cluster which include both batch, like experiment batch 1, experiment batch 2. If your cluster, for example, if the cluster 1 include both batch 1 and batch 2, and if there is this kind of the like difference, like sequence dips or something, maybe the CellOracle will detect, will do something wrong based on the difference of the batch stuff. So this is the worst case scenario. I mean, if you split the data set into the different batch and do the GRN analysis separately, which is no problem. But my concern is if you merge two data set and just pick up one cluster and do the single cell, do the GRN inference, maybe this will be affected by your batch. So this is gonna be the really worst. I mean, you will get like long connection because of your batch or something. So this is the worst case scenario.
I'm thinking this is something we could maybe look into and use existing data sets to explore what the impact of batch is on these inferred GRNs.
Yeah. Okay. So for next week, I will make some presentation slide to explain my concern. So I will explain in detail.
That would be really helpful.
Yeah. So I mean, we are using some mass model or machine learning model, which we need to be careful about the feature of this model. So I will explain in detail in the next meeting, next presentation.
Anybody else have any questions?
Yeah, go ahead, Sarah.
Mine's just a really quick general usability question here. You mentioned that when you actually calculate the GRMs, that it takes a good bit of time. Can you talk at all about memory allocation on that step? Because that's something that I've run into a little bit. Do you know much about how much memory it actually takes to run the GRNs?
Yes. So I think it's not too much, I guess. I mean, so the GRN inference will use maybe, I don't know, I think it takes less than 8 gigabyte, I think, like 4 or 5, I don't know. The most memory, in the last part, in the simulation part, it will use a lot of memory, maybe which is the most memory consuming part. So, but GRN inference itself doesn't use memory, I think, too much memory, I guess. Yeah, so like if you have like 50,000 of cells, or if you have like no, not 50, like 500,000 cells, maybe it will take like 64 gigabyte memory on the simulation part. It's gonna be really big. But if you have like 2,000 cells or like less than 10,000 cells, maybe you need just like 8 or 10 or something.
Great, that's helpful. Thank you.
Yeah. So I had a question, Kenji. So let's say I have a single cell RNA sequencing data, and let's say I'm not sure about how good its quality is. Maybe there's like a lot of dropout or noise or something, and I run it through the CellOracle pipeline. Is there like one, or do you think it's possible to have like one quantitative metric to see how confident I can be in the network that is inferred? Like once I create a network using CellOracle, is there a metric which I can look at that, okay, it ran well on my data set or it did not run well on my data set?
Yeah, it's kind of hard question. So maybe one good metric you can look at is like degree distribution. So like Sam mentioned, you maybe you will get like scale-free network structure. So this is one thing you can look at. The second is like the the best metric is if you know about the biological system, maybe you can look at something. If you know like this transcription factor is supposed to have many connections, so you can look at this transcription factor. Maybe this is the best validation. But if you have no idea about the biological system, I think it's kind of hard to know your journey is going well or not.
Yes, one thing we did in the paper was, really look at the network inference and compare that to ground truth data. So inferring GRN from liver, and then actually taking a transcription factor. In that case, it was HNF4 alpha, and comparing the ChIP-seq. Comparing those top targets with each other. But then, like as Kenji said, in unique biological systems, you're not necessarily going to have that ground truth data to hand. But these are really good questions for users.
Yeah, I was just wondering because this is some issue I run in with other analysis where I do that, but then I don't have like definitive QC metrics to look at. I'm not sure whether it worked or not. I was just wondering. But yeah, I agree that this is a very hard problem to solve.
It'd also be ideal to generate some data or take some really bad data and look at the networks that are inferred, or take a good data set, downsample it, and see at what point did these networks start falling to pieces exactly, and then we could use the HNF4 alpha ground truth data and compare that to the inferred GRNs from liver, and start seeing where, and then people can get an idea of how to read the degree distribution, or look at the targets, and
one thing you could also look at is what happens if you reduce the total number of cells from the same data set, and how like the network inferred changes.
Yep, I agree.
Cool, thanks.
Okay, any more questions? Okay, so the result at this point is you've pre-processed all your data, you're getting everything ready for the simulation, which may come next week or the week after, depending on how many questions I'm asking. And you've inferred your network. So essentially, for each transcription factor, you get a list of genes that it's targeting. And one of the problems that CellOracle overcomes is to actually help you interpret these networks. So next week, Kenji's going to be diving into some of the, taking these ideas from graph theory to actually dive into these networks and give us some interesting biological conclusions from these data sets. Thanks, Kenji.
Yeah, thank you.